Welcome to the deep dive. Today we're getting into something pretty critical, looking at some really advanced science on how flash floods actually affect buildings.
That's right. We're looking at a specific study here from Fracture and Structural Integrity. It's titled Flood-Induced Load Effects on Real-Scale Structures, a 3D multi-level dynamic analysis. Quite a mouthful.
It is, but the core idea is fascinating. Think of this deep dive as, well, getting you up to speed on how these sophisticated computer models are changing our understanding of building vulnerability, especially with flash floods becoming more intense.
Exactly. The mission, if you like, is to unpack this, see why older methods maybe weren't quite hitting the mark, and what this new 3D approach really tells us about the forces involved.
Okay, so flash floods, we know they're dangerous, obviously, but this research really zeroes in on the suddenness and the sheer force, doesn't it?
It really does. And with climate change driving more severe weather, the risk, particularly to certain types of buildings like masonry structures, is definitely going up.
Why masonry specifically? What makes it so vulnerable here?
Well, flash floods aren't just rising water, they're violent surges. Masonry, because of its properties, its weight, and how it's constructed, is quite susceptible to those hydrodynamic forces. The power of the moving water itself and also getting hit by debris, sediment, all that stuff carried along.
Right, the impact. So
Mhm.
before we had these kinds of advanced simulations, how did people figure out if a building could handle a flood? What were the traditional ways?
Good question. Traditionally, it was mainly through what are called indicator-based methods. Think of it like trying to predict, I don't know, a race outcome using just a few stats.
Okay.
They use things like vulnerability curves, trying to map flood intensity to likely damage, or damage matrices, which are more qualitative, looking at past events.
So based on what happened before to similar buildings?
Sort of, yeah. And also vulnerability indicators,
Yeah.
specific features of a building you can measure, things thought to affect its resistance.
So kind of a checklist approach, maybe, using historical data. What's the problem with that? Sounds reasonable on the surface.
Well, the big issue is oversimplification. These methods, while easier to apply maybe, they just don't capture the complex physics of a sudden flood hitting a structure.
Hmm.
They often focus on limited building types and that reliance on historical data. The study calls it out historical limitations. Things change, right?
Mm.
Building codes, land use patterns.
Sure.
Plus, getting good, consistent data is hard. Standardizing it, deciding how much weight each factor gets, it's tricky. And crucially, they often miss the sheer dynamic intensity of the event.
That makes sense. It's not just water level, it's the force of the moving water. So how do these newer simulation methods improve things?
Simulations give us a much more explicit picture of the physics, what's actually happening when water hits the wall, how that translates to stress and potentially damage within the structure.
And this study introduces a specific type.
Yes, this novel 3D multi-level dynamic analysis. It sounds complex, but the key is multi-level. It looks at the problem at different scales, kind of zooming in.
Okay, different scales. Like a wide view and then a close-up.
Pretty much.
Yeah.
At the macro scale, the big picture, they use CFD, computational fluid dynamics. Imagine a really detailed simulation of just the water flow hitting the building, treating the building itself as completely rigid initially.
So just how the water behaves around a solid obstacle.
Exactly. This gives them precise forces the water exerts. Then, at the meso-scale, the structural level, they take those forces calculated by the CFD
Right.
and apply them to a detailed computer model of the building. This model predicts how the actual materials will respond, cracking, deforming.
Mhm.
Uses something called a coupled damage-plasticity model.
So first, water hits a rigid thing. Second, apply those calculated forces to a model of the thing that can break. It's a one-way coupling.
Correct. For this study, yes. The fluid simulation informs the structural one. The flu part uses complex math, Rans-S equations, a K-epsilon model to track turbulence and the air-water interface. It's quite sophisticated stuff.
And the building model itself, what makes that special?
That coupled damage-plasticity model is designed specifically for materials like masonry. It captures both the weakening from cracking, the damage part, and permanent deformation under compression, the plasticity.
Okay.
Now, they do make an assumption here. They model masonry of reasonably good, consistent quality. They acknowledge that for, say, older historical buildings with weaker mortar, the failure might look different, perhaps more localized.
Got it. So focusing on the fundamental interaction with the sound structure, what did they find when they ran these virtual floods? What happened to the virtual building?
Well, first at the macro scale, they track the pressure on the front wall over time. Really interesting pattern. There's the bit before impact, then the sharp peak load as the water hits, and then a phase where the flow stabilizes around the building.
That peak sounds important. How did that compare to what the older methods might predict?
Ah, this is a key finding. They compared their dynamic results to quasi-static approximations, those simpler calculations that don't really account for the sudden impact, and also to older 2D models. And the simpler methods significantly underestimated that initial peak load, that first big hit. They also found the area under the highest pressure was smaller in the static models. The traditional quasi-static formula, even with its dynamic coefficient, just couldn't capture that transient spike.
So that initial slam is much stronger and more focused than we thought based on simpler math.
Precisely. The visualizations they produced really show it. You see the wave hit, pressure shoot up, then gradually settle.
Okay, so that's the water side. What about the building's response in the model? How did it handle those forces?
Well, the loading curve on the building model closely followed the pressure curve from the fluid simulation, which is good. It shows the models are linked correctly. When they compared the building's response under this dynamic load versus a simplified static load, they found the dynamic model only started looking similar to the static one after the flow stabilized. And even then, there was still about an 11% difference in the overall force.
So static models were more conservative, maybe, for the sustained force later on. But what about the initial hit and the immediate damage?
That's the critical bit. The dynamic simulation showed much greater out-of-plane displacement, the wall bending outwards right after that peak load hit. The quasi-static models underestimated this key displacement by roughly 28%.
28%? That's huge, because they missed the peak impact.
Exactly. And here's something interesting, maybe counterintuitive. The maximum damage in the model didn't happen right at peak pressure.
Oh, when did it happen?
It actually occurred a bit later, during that stabilized flow phase. It suggests that the duration of load, even if slightly lower than the peak, allows the damage to accumulate and grow.
You think the biggest hit causes the worst immediate damage?
You would, wouldn't you? And the pattern of damage was different too. The dynamic model showed damage spreading out from the center towards the edges, which fits how we expect masonry walls to fail under sideways force. The static models showed more concentrated, localized damage.
So the dynamic simulation gives a totally different picture of how the failure progresses.
It really does. It highlights why capturing that dynamic effect is so vital for realistic predictions.
Okay, so the dynamic model seems much more insightful. Did they also look at how things change under different flood conditions, like deeper water or faster flow?
Yes, they did a parametric analysis, systematically changed the water depth and the inflow speed, ran the simulations again, and looked at the load capacity, the displacement, the damage patterns for each scenario.
Smart. What did varying those reveal?
Well, at lower depths and speeds, the dynamic and quasi-static results were actually more similar. The differences really emerged as things got more intense. As velocity and depth increased, the dynamic model consistently predicted much higher peak loads. It really drove home the importance of that initial impact force, which the static models just don't capture well.
So the gap between the methods widens as the flood gets worse.
Exactly. The quasi-static approaches increasingly underestimated both the peak pressure and the maximum displacement under more extreme conditions.
Makes sense. What about the damage patterns?
The damage map showed much more widespread damage at higher velocities in the dynamic model, looking much more like the kind of real-world collapse mechanisms we might see. And under the most severe conditions, high depth, high velocity, the dynamic model actually predicted complete structural collapse.
Wow. Did they find if speed or depth was more important?
Interestingly, yes. They found that the water velocity was the main driver for the peak structural loads of that initial impact force. But the water depth had more influence on the extent of the damage and the eventual failure mechanism.
So speed delivers the punch, depth determines how much breaks.
That's a good way to put it. Speed for the peak force, depth for the overall damage pattern and severity. This parametric study really hammered home the limitations of static methods and the need for dynamic analysis for accurate assessment.
Okay, we've covered a lot of ground here, really digging into this 3D multi-level dynamic analysis. What's the big takeaway message from all this?
I think the core insight is that this kind of advanced simulation gives us a much more accurate and detailed picture of what happens when a flash flood hits a masonry building compared to the older methods.
And its main advantage is capturing those dynamic effects.
Absolutely. That initial impact, the transient peak loads, that's what simpler models often miss, and this research shows just how crucial that is.
And why does getting this right matter so much? What are the implications?
Well, look around. These extreme events are happening more often. We desperately need better tools to figure out which buildings, which bits of infrastructure are most vulnerable. More accurate modeling like this leads to better risk assessments. That means we can potentially target interventions better, strengthen the right places, maybe save lives, definitely reduce damage costs. It's about smarter preparedness.
So thinking ahead then, with these kinds of powerful events likely increasing, how could these advanced simulation methods really reshape how we approach designing and protecting things in flood zones?
That's the big question, isn't it? You could see it influencing building codes, material science, construction techniques, all informed by a much clearer understanding of the actual forces involved.
And could this type of detailed modeling be useful for other kinds of natural hazards too, beyond floods?
Oh, absolutely. The potential is huge. Think about storm surges, tsunamis, other events involving powerful fluid forces,
Yeah.
or even different types of sudden impacts, like extreme wind loading. Applying similar sophisticated dynamic modeling could give us breakthroughs in understanding and mitigating risks across a whole range of hazards. Really opens doors.